Hello, am I audible?
Not audio.
Yes, sir.
Now is okay.
Yeah. So I think I got out of the class. Okay. So choose the correct option from the following. These are the four options. So we have been given two things. One is small data set and another one is large data set. Okay. Hello. Yeah, small data set, large data set. So we have two things. Whenever we are considering small data set, what we want is small data set means there will be error because we are considering less data points. So there will be error, but we want our variance to be small. So for that, for this, for small data set, if we consider this two statement, for small data set, one should prefer a high bias low variance classifier. Okay, our variance should be small for a small data set, but whenever we are considering large data set, we know there will be variation in our data because this is a large data set. There will be a variation in our data, but we want our model to have a low bias. Okay, so for large data set we want low bias but high variance. Okay, so so correct answer is B and D. Okay.
Okay, sir.
Okay. Now let's start. Let's see question number 8. Consider the following statement. Statement A: in forward stepwise selection, in each step that variable is chosen which has the maximum correlation with the residual. Then the residual is regressed on that variable and it is added to the predictor. Statement B: in forward stage-wise selection, the variables are added one by one to the previously selected variables to produce the best fit till then. So option A is both the statement are true. Option B, statement A is true, B is false. Option C, statement A is false, B is true, and option D, both the statement are false. Yeah, someone is telling both false. Any other guesses? Yeah, absolutely right. So here, what happens is they have changed the definition. Okay, they have reversed the definition. In forward stepwise selection, this is the thing. The variables are added one by one to the previously selected variables to produce the best fit. In forward stage-wise selection, this is the thing. In each step, the variables is chosen which has the maximum correlation with the residual. Then the residual is regressed on the variable and it is added to the predictor. Okay, so they have reversed the statement. So that is why both the statement are false. Okay, this is the true statement. You can check, and so the correct answer is D. Okay, is it clear?
Okay.
Okay. Now question number 9, the linear regression model y equals to a naught a1 x1 plus a2 x2 plus ap x plus dot ap xp is to be fitted and training data points having p attributes. Let x same thing with one vector of target. Okay, theta, yeah, here they have instead of beta they have added theta, and theta is your a naught a1 a2 ap. Okay, this is your theta. If the sum squared error is minimized for obtaining the optimal regression model, which of the following holds? So same thing, whatever we have done the derivation is the same thing. Let's see, let's focus on to here again. So yeah, so this is the thing, they have asked the same thing again. So here they have just yeah, they theta they have called theta of for beta naught beta 1 beta 2 etc, and instead of beta naught they have used a naught a1 etc. Other things are quite similar. Okay, same thing. So we will again do the same steps. Yeah, we will again do the same steps. So xtx xy, yeah, these are the four options. So yeah, we will be calculating residual sum of square error with respect to theta here. Earlier it was beta, now it was theta. So this is your formula. We already know that we have to take derivative, and once we take derivative, we will come out of we will be coming to this x transpose y minus x theta. Okay, so you can open it x transpose into y minus x transpose into x into theta. Okay, so you can so when we will open it, that will be equals to x transpose into y equals to x transpose x theta. So this will be your answer, and your right answer will be option D. Okay, so it is clear, right? Same question here, instead of beta, they have taken theta. Okay, same thing. It is clear, right?
Yes, sir.
Okay. So let's move on to the last question. Let A be m cross n be a matrix of real numbers. That means A is a matrix with m rows and n columns. Okay, the matrix AAT, A transpose has an eigenvector x with a eigenvalue b. Okay, then the eigenvector y of ATA. Now they are asking reverse. Okay, they have given eigenvector an eigenvalue of this matrix, and they are asking reverse. Okay, eigenvector of x with eigenvalue b. Okay, then the eigenvector y of ATA, which has eigenvalue b, is equal to, option A is xTA, option B is AT, that means A transpose x, option C is x, and option D cannot be described. Okay, so we have to solve this. So how we will solve this? We know this. Okay, what is this? We know a matrix into its eigenvector is equal to eigenvalue into eigenvector. Okay, this is a thing of matrix. Okay, this thing we know. Now we, how to solve it? We will multiply AT on both the sides. Okay, that is, we will multiply by A transpose, and when we will multiply by A transpose, we will get this A transpose into this thing equals to A transpose into BX. Okay, now we are asked to find eigenvector of ATA. Okay, eigenvector of this matrix ATA. So our matrix should be ATA. So we are just putting ATA here, and then this A we are shifting it to with x. Okay, so ATX equals to B into ATX. Now again this is of this form, that means matrix into vector, eigenvalue into eigenvector. That means the eigenvector of this ATA is equal to ATX. AT means transpose. Okay, okay, so the correct answer is B. Okay, so is this clear? This question is clear, right?
Sir, can you repeat it once again?
Yeah, here in the question it has been asked that we have a A matrix with m cross n. Okay, m is number of rows and n is number of columns. So we are matrix of real numbers. Okay, the matrix AAT has an eigenvector x with eigenvalue b. Then the eigenvector of y of ATA, which has the eigenvalue b, is equal to this. That means we have a matrix, we have been given eigenvector and eigenvalue of that matrix. We have been asked for another matrix, what is the eigenvector of it if eigenvalue is given. Okay, so how we will solve it? We know that matrix into eigenvalue, okay, matrix into eigenvalue is equal to matrix into eigenvector is equal to eigenvalue into eigenvector. Okay, this is matrix, this is vector. Okay, this is okay, vector, let me put VE, VE. Okay, this is VE, and this is value VA, this is VA, and this is VE. So matrix into vector, eigenvector is equal to eigenvalue into eigenvector. Okay, this V is your vector, VA is your value. So this is applicable for all the matrix. Now we have been asked to find the eigen vector of this matrix. Now how we can solve it? A into AT we have been given eigenvector as well as eigenvalue. So here what you can do, here you can multiply this matrix with AT. Why we are multiplying this with AT? Because we want ATA, but we have AAT. So once we multiply it by AT, that is A transpose on both the side, we will get this. Okay, now if we can take this two ones and this two ones, similarly if we can take B here and ATX here, then we can get this equation. That means now we have ATA into ATX equals to B into ATX. So ATX can be considered as a vector, this VE. ATX is considered as a vector VE. Okay, now ATA is your matrix, and B is the eigen value. Here eigen value is given B, so B is your eigen value. Now we are asked to find what is the eigen vector. The eigen vector will be ATX. Okay, so eigen vector will be equal to ATX. Okay.
Okay, sir. Thank you.
Okay. Any doubt?
No, sir.
No, sir. Thank you so much. Sir, can we get the YouTube for this, right?
Yeah.
That will be there. No,
Yeah.
if you want to revise on something else.
Yeah. So let me again revise it. We have 30 more minutes. So who want to stay can stay. Who want to leave can leave. Okay, this will be in the YouTube channel. Okay. So if you want to stay, you can stay. So let me again revise it. Okay, 30 or 1 hour. You can leave. Others can maybe leave if you want. Okay. So this is the thing. So I have started with this. All models are wrong, but some are useful. Okay, that means all the I am telling all the machine learning models are wrong. Why I am telling this? Because every model has some error. Nothing can have zero error. If we have zero error model, it is overfit model. Okay, overfit model means when you are testing it on a real data set, that it will not give right prediction. Okay, so all models are wrong, but some are useful. Okay, so this is one of the popular saying of this machine learning model. Okay, now linear regression model and least squares. Okay, so this is a thing, xt equals to x1 x2 dot x p. So let's delete this. Okay, so yeah, so this is our input. So let's take this example. We have x1 x2 Yeah, those who want to leave can leave, otherwise you can stay. Again I am revising it. Okay, some may have joined late, etc. So again I am revising it. This I will be putting on my YouTube video, so you can probably see it. Okay, so this we have x1, x2 and we have x1, x2, and let's say x3. We have three inputs, we have one output, that is y. Okay, we have n number of data points, 1 2 3 4 5. So we have n cross p plus 1 is our x matrix. X matrix is n cross p plus 1. Okay, so 1 2 3 4 5. Okay, x1, x2, x3. Okay, now we are fitting a linear regression model. So our linear regression model will be equal to fx equals to beta naught plus plus x1 beta 1 plus x2 beta 2 plus x3 beta 3 plus x dot 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 xp beta p. So we have p inputs. So we are going from j from 1 to p. Okay, so this is our model. Okay, now we have got our model, but we are required to find the beta so that our model best fit. Okay, for best fitting our model we have to find the beta. Okay, yeah, we have to find our beta. Okay, yeah. So how we can find the residual square error? We can find out the residual square error. These are the actual values. Okay, this y is the actual or yi. Okay, but fxi, this fxi is the predicted value. So we have actual value, we have predicted value. Now we can find the residual sum of squares, and that how we can find out? We can, hello. Yeah, that how we can find out? We can find out by y minus f of xi. Okay, so yi minus beta naught equals to j equals to 1. Yeah, so fxi, we have put the fxi from this equation. We have put the whole fxi here, that is yi minus beta naught minus from j equals to 1 to p xij bj whole square. Okay, so this is the thing we have put. Now this is our square error. The one thing can be your doubt, that why we are interested in square error, why we are not interested in only error. Only error is your predicted minus actual minus predicted. So we can write our error as yi minus fxi also, and sigma, and sum it for all the data points. That we can do. But why we are doing it for why we are squaring the error? Okay, that can be a question. So if we do not square this error, if we just do yi minus f xi, and we are adding it for all the data points, there can be some data points for which this error thing can be positive, and some other data points this error things can be negative. Okay, so this is a problem somewhere. So to encounter this problem, we are squaring the error. That is why we are talking about residual sum of the squares. Okay, so residual sum of squares with respect to beta, because beta is our variable. Okay, beta is our variable by which we will fit the model. So we are interested in finding this RSS beta, that is yi minus fxi. Fxi, I is a data point from 1 to n. That means, let's say we have 5 data points, so I will be equal to 1 to 5. Okay, this is your RSS beta, that means residual sum of square with respect to beta. Okay, and when we are opening the fxi, you will get this equation. So up to this it is clear. Now what we are interested to do this thing in a matrix form. Okay, because here we can visualize it. If we have only one input, we can visualize it, but if we have more input, it is necessary to convert our this data points into some kind of data points into a matrix form, so it can be easily visualized. So for that, let's say this is our thing. So we have 5 data points. We have 3 inputs. Okay, so we will make our X matrix or the input matrix as n cross p plus 1. N is the number of data points. That means 5 cross p plus 1. P is your number of inputs. So we have number of inputs 1, 2, 3. That means p will be equal to 3. So 5 cross 4. Our x will be equal to 5 cross 4. Similarly, our y will be equal to y will be equal to n cross 1. Okay, y will be equal to n cross 1. So for this, y will be equal to 5 cross 1. Okay, so these two are our matrix of importance. One is x and another one is y. X will take the input, y will take the actual outputs. Okay, these are the two matrices of importance. Okay, now there can be a question why we are taking p plus 1, why not only p. This is usually a question why we are using p plus 1 and not p. Okay, so thing is, here you can see the equation. This equation has an extra term beta naught. Okay, that is not related to any input, but that is some kind of intercept. So for accounting it, we are taking this beta naught. Okay, so that is the thing. So beta naught will be this thing, j equals to 1 to p x j bj. So to counter this beta naught, we are taking p plus 1. Otherwise we can take n cross p, but as we also want the intercept to this fx equation, that is why we are taking n cross p plus 1, and our y will be usual output, that is n cross 1, that is 5 cross 1. So this thing is only written. Now whenever we are converting this equation into a matrix form, our equation will be this. RSS beta will be y minus x beta. Y is your matrix of the output row, actual output row, minus x will be your input matrix. Beta is your beta matrix will take all your beta into account, that is beta naught, beta 1, beta 2, etc., etc., and y minus x beta. So that will be your residual sum of square thing whenever you are considering matrix. Okay, matrix. So that this equation will be converted to this equation. Now thing is del by now your thing is how we can say our model is the best fit model. We can say our model is the best fit model when our RSS will be minimum, that is residual sum of square error will be minimum. So whenever our residual sum of square is minimum, for that model we can say this is our best fit model. So our idea is to minimize this RSS with respect to beta. Okay, so how we can do that? We can do this by differentiating this RSS with respect to beta and then equating it with 0. Okay, so we are differentiating it and then we are equating it to 0. Okay, so this whenever we will do this, we will be getting our we will be getting this this equation. Okay, whenever we are differentiating this with respect to beta, we will get this. Okay, so minimizing the RSS. How we can minimize the RSS? If we equate this this differentiation value of RSS with respect to beta with 0, by this we can find out the beta. Remember, beta is a matrix that take beta not beta 1, beta 2, beta n. Okay, so by that we can when we will solve this, we will get beta matrix as xt into xt, that is transpose of the x matrix, into x matrix inverse of this into x of transpose into y. Okay, so we found the beta. Once we found the beta, we can put all the beta in this equation and we can find the fx. Okay, fx, we can find the fx. Okay, so once we found the fx is also called y hat. Okay, fx means predicted value, that is why it is called y hat, and this is your only y is your actual. Okay, so this is the difference. So fx is the predicted value, that is why we are putting a hat. So fx or y hat will be equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus dot 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 beta x beta p x p. So we will find our beta values for our best fit model, and we will find our equation for our best fit model. Okay, so this is the linear regression and least square method. Okay, now second, what I have discussed, the linear regression model example with inputs. Okay, so here you can see you got the concept. Now we will be discussing one example. Okay, in previous slide only I have told you that let's take a linear regression model that is dependent on three inputs, right? X1 x2 x1 x2 x3. Now let's take a real example. In real example also, your fx is equal to the weight of a human. Okay, and that is dependent on to three input parameters. Fx is your output parameter, and that is dependent on three input parameter. X1 is your sex, x2 is your age, and x3 is your height. So this is an example of a linear regression model that we have just discussed, right? So fx is equal to b naught plus b1 x1 plus b2 x2 plus b3 x3. Previous slide we have only told b as beta. That is the only difference. So we have a linear regression model with all these three things: sex, age, and height. Okay, now there are there are seven possible models we can use. We can derive from this machine learning model. Okay, how we can derive seven possible model? We can take only one parameter, only one input parameter, that is sex. Okay, so we can take only x1 and we can eliminate all this. Okay, so fx will be equal to beta naught plus b1 x1, where x1 is your sex. Okay, that becomes a model. Second thing, we can only take age. Third, we can only take height. Fourth, we can only take sex and age. Fifth, we can take sex and height. Sixth, we can take sex, age and height together. And last, we can take the full model, that is we can take all the inputs together. So why I am discussing this? I am discussing this because a bigger model can be treated as several smaller models. Okay, so from this bigger model we have made seven subset of this bigger model. Okay, so first subset we are only taking sex. Similarly, second subset we are taking age. Third subset only height. Fourth subset we are taking sex and age. Fifth subset we are taking sex and height. Sixth subset age and height. Seventh subset sex, age, and height. Now 1 to 6 model are known as reduced model, because we are not using all the three input parameters. We are reducing one or two input parameter. That is why it is called a reduced model, or sometimes called the nested model. But last model is called as full model. Why it is called full model? Because we are taking all the input parameters. That is why it is called full model. Okay, so that is the difference. So first six are called reduced model or nested model, and last model is called a full model. Okay, now dimensionality of inputs. Now thing is, whatever we have till now discussed, we have only discussed about three input parameters, but there can be real scenarios in which the input parameters can vary, like it can go more than 100 or etc. Okay, so this is a okay, someone wants to join the meeting. Okay. Yeah. Now, dimensionality of input. Dimensionality of input means, dimension means number. Okay, so dimensionality of inputs means number of inputs. Now for small model it is okay, up to 3 inputs it is okay. But there can be real life problem in which the inputs can go to more than 3. The inputs can even go to 100 or 1000, maybe 1000. Okay, so in that there is a problem of dimensionality. Okay, dimensionality means number of inputs, that you understood. Now if the input is increased, like the input is increased from, let's say previous we have only 3 inputs, but now the input increased from 3 to 1000. Okay, there can be a case. Okay, the inputs increase from 3 to 1000. Now this is a problem. Okay, the inputs, when the inputs will be increased from 3 to 1000. Now the problem is, if the input is increased from 3 to 1000, it is first the problem is it is more time to compute, because whatever we are discussing not for only mathematical calculation by hands. Okay, we want all these things to incorporate in a computer or machine. Okay, so if our input will be increased, our machine will take more time to compute. Okay, so this is a problem. Second thing is more memory to store input and intermediate results. Definitely, if input will increase, it will take more memory to the system will take more memory to store the inputs as well as the outputs or the results. Okay, third problem, more complicated explanation. Because machine learning, we are not just making a model, we are also wanted to interpret the model. Like, we are interested in interpret the model. That means we are interested in how much this weight is dependent on sex, how we can interpret it by this coefficient beta or beta 1 or b1. Okay, by this we can interpret it. That means the weight is dependent on sex, how much, the weight is dependent on age, how much, the weight is dependent on height, how much. Okay, so we can interpret it. But as our model size increases, or as our dimension of input, number of input or dimension of input increases, the interpretability is a serious concern. We cannot interpret it well. Okay, because it is basically difficult to interpret. Like, if we have two parameter, we can interpret that weight is more dependent on height than weight is dependent on age. Okay, we can interpret like that. But if we have 100 parameters, we cannot interpret it well. So this is again a problem. Last is no simple visualization. Remember, any data we are taking, we are visualizing it. Like we have this x1, we have this x1 as input, so we can visualize it by two axes. We can visualize it. X1 we will put the input, and y we will put the output, or y equals to fx. Y equals to this, y equals to actually fx. So y we can visualize this data well. For one input we can visualize it by two axes. Okay, for two input we can visualize it by three axes. But if we have 100 input, how we can visualize it? So again, this is a problem. So this is a curse of all this thing is called curse of dimensionality. Also one thing, and the problem is we required more number of data points. Like this, you see this 1 million of 1D inputs is not equal to 1 input of dimension 1 million. What does this means? See, if we have 1 million data points of one input, okay, that is not a problem. But if we have if we have 1 million input and only we have one data point, that is a serious problem, because by that we cannot fit our curve, because only we have one data point for one input each. So we cannot fit our curve. For fitting the curve, at least we required 3 to 4 data points, right? It is a basic mathematics. For fitting a curve, we require 3 data points, right? So one data points we cannot fit our curve. So okay, okay, okay. So this is the thing. So all this thing is called curse of dimensionality. Curse of dimensionality means if number of input is increased, there are various problems. What are the problems? I am again repeating. It is, first is more time to compute, second is we require more memory, third is difficult to interpret, fourth is no simple visualization, and this last is yeah, curse of dimensionality, that is we require more data. Like earlier we have three inputs, we have 5 data points, it is okay. But okay, let's leave that example, let's see this example. Like if we have one data point, if we have one input and we have 1 million data points, it is easy to fit the curve. But what will happen if we have 1 billion input and we have one data point? We cannot fit the curve, because we also know that for fitting a curve we require 3 data points. So both these things appear similar. Like 1 million into 1, that means we technically have 1 million points. Here also we technically have 1 million points, but problem here is we cannot fit the curve in this, because we cannot fit the curve in this, because we have 1 million, because we have only one data point for one input. So for fitting any curve, we know that we require at least 3 data points, so we cannot fit the curve. So these are the dimensionality of inputs. Now to encounter this, we have two things. One is feature selection and second is feature extraction. Now what is this feature selection and feature extraction? Now how we can come out from this curse of dimensionality? We can come out this curse of dimensionality is we can select some of the feature. That means we can consider only some of the inputs. Like we have 100 inputs, but we have 3 inputs are our prime importance. So we can keep these 3 inputs, we can eliminate the 97 inputs, or we can eliminate the 90s, we can keep 3 inputs, we can eliminate the rest 97 inputs. Okay, so this is this is called feature selection. Okay, so feature selection means we can drop some features, and first we have to estimate which features can be dropped from the data. So features that are less important, we will drop it. Features that are more important, we will keep it. Okay, so this is feature selection. Second is feature extraction. Okay, feature extraction means, yeah, we are considering all the 100 inputs only, but out of the 100 inputs, we have found that some inputs are correlated with some inputs. So those inputs which are correlated, like one case, age is related to height. Okay, so age and height are very much correlated, so we can only keep height. Age and height are very much correlated, so we can make another variable that will take this age and height together. So okay, so we are like you can see this. Yeah, you can see this. We have three parameters, like sex, age and height. So here, if there is a case in which sex and height are very much related to each other, so we can feature selection means we are selecting one feature. Like we are selecting some feature and we are dropping the other feature. These 6 cases are example of feature selection. Like we are here only considering sex, we are considering age, we are considering height, and we are eliminating or we are not considering the other features or other inputs. So these are feature selection. But there can also be some case in which sex and height are very much correlated. So I can reduce the dimension, or how I can reduce the input. I can take age plus something called let's say I will take it as SH. This H is SH, age plus SH. Okay, this SH will take account of sex as well as height. So that thing is called feature extraction. So again I am repeating, there are two things. One is feature selection, feature extraction. Feature selection means we are keeping some feature, we are dropping the other feature. That is feature selection. Feature extraction means we are making feature out of some correlated features. Features means input. Okay, don't get confused. Feature means input. Okay, so feature extraction means we are making inputs out of correlated inputs. Okay, like age and like sex and height are very much correlated, so I have made an input called sh that will take account of sex and height. So by that I have reduced the dimension. How I have reduced that dimension? Here the inputs are 3, but here the inputs are 2. So that is feature extraction. I have not dropped anything, but I have out of this sex and height I have correlated this sex and height, and I have made one input called sh. Okay, so by that I have reduced the dimension. So that is feature extraction. But if I made a model only by age, that is feature selection. That means I am removing the sex and height. So that is feature. This model will be called feature selection model, and this model will be called feature extraction model. Okay, so this is the difference between feature selection and feature extraction. So these are mathematics. Hello.
Sir, in simple words, we can say feature extraction means we are going to merge with the correlated.
Merge with the that is feature extraction. Okay,
Extraction. Selection means?
we are dropping. Simply we are dropping.
Yes. Neglecting that.
Yeah, simply we are dropping a feature.
Yes.
Okay. Okay, any more doubt up to this? Some people still are here, so any doubt up to this? Anyone wants to ask anything? Okay, already I have explained, but again anyone if you want some more explanation, can please. Okay, okay, no problem. So this is the feature extraction and feature selection thing. Okay, now feature selection, there are algorithm for feature selection called subset selection algorithm. Okay, so what is this subset selection algorithm? Subset selection algorithm, two reasons why we are not satisfied with this least square estimate. One is interpretation. I have already discussed that if we have a curse of dimensionality, we have more dimension, then interpretation is a problem. Second, there can be a prediction accuracy. There can be a problem of prediction accuracy. How there can be a problem of prediction accuracy? See, what happens is that some of the inputs are not related to the output. Okay, like if in a problem of this weight equals to a sex and height, if I put an input called cost. Okay, so this cost input, cost or income input. Okay, let's say income input. Okay, if this I put a income input, this income input is not at all related to our output. Okay, so this income input will definitely have this income input will definitely affect our prediction accuracy. So for that we will go for this subset selection. Okay, subset selection, there are three methods we can do this subset selection. One is forward stepwise selection, second is backward stepwise selection, and third is forward stage-wise regression. These are the three things by which we will do this subset selection. Yeah, subset selection is a type of feature selection. Okay, so what is this forward stepwise selection? Forward stepwise selection, whenever we are discussing about this forward stepwise selection, see, forward stepwise selection, we are starting with the like you see this. Yeah, if we'll do forward stepwise selection in this, we will start with only beta naught first. Okay, we will make a machine learning model fx equal to beta naught. Okay, this is forward stepwise selection. That means we will be starting with the intercept, and then we will add on to our input one by one. For after this is one model, right? Fx equals to beta naught. Okay, this is one model, and by this model we will find the RSS. Okay, RSS. This model we will find the RSS, and then we will keep on adding the input. Like our second model will be equal to Fx will be equal to beta naught plus beta 1 x1. Similarly we will add our input one by one. Okay, so why we are doing it? We are actually interested in dropping the feature. Okay, so if we find that RSS is RSS is better in first model, and after adding a feature the RSS actually increases, that means error is actually increases, so we will drop that feature. Okay, similarly we can try it with all the inputs. So wherever our RSS is actually increasing, that means error is coming more, so that means that feature is not good for our model, so we will drop that feature. Okay, so by that we can do the forward by that we can do the this thing, forward stepwise selection. Second thing is backward stepwise selection. Stepwise selection is reverse of forward stepwise selection. In backward stepwise selection we will be choosing our whole model at once, like Fx will be equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x2. In forward stepwise selection, what we are doing, we are starting with only intercept, but backward stepwise selection we are starting with the whole model, and then what we are doing in backward stepwise selection, we are eliminating one by one feature one by one. In forward stepwise selection we are adding feature one by one, here we are deleting feature one by one. Okay, so by that we can do our subset selection. This is the second method. We have a third method called forward stage-wise selection. In forward stage-wise selection, we start with our forward stepwise selection. That is, we start with our intercept. Okay, we start with our intercept, and we then add a feature or add a input, but we will add that input that is closely related to our residual of the previous thing. That means we will start with let's say here, we will be starting with our intercept, that is beta naught or y bar, anything you call. We will start with our intercept, but then we will be adding that feature that is closely related to our RSS1. Okay, we will be selecting that feature only that will be correlated to our RSS1. Okay, in forward stepwise selection, that is the first method, we are not doing this. We are just randomly or we are just sequentially selecting input one by one, but here we will select that input only that is closely correlated to our RSS1. Similarly, we will select another input that will be closely related to our RSS2. By that we can do this. Okay, so this is the thing. About this subset selection. So we have three methods. Again, I am discussing forward stepwise, backward stepwise, and forward stage wise. Forward stepwise, we will first start with the intercept and then add feature one by one. Backward, okay. Backward stepwise selection, we will be considering our whole model at once, and then we will delete the feature one by one. Forward stage-wise selection, similar to forward stepwise selection, we will start with the intercept, and then we will be adding feature one by one, but that additional feature must closely correlate with the residual of the previous input or previous intercept. Okay, that is the concept. So this is subset selection. But subset selection, there are several disadvantages. One disadvantage is it is a very discontinued it is a very it is a very discrete step. Discrete step means either we are considering a variable, either we are considering input, or we are simply dropping it. So it is very discrete. Okay, so how we can make it continuous? So we can make it continuous if we can make it continuous if we can select all the feature, but we can shrinkage the coefficient. What does that mean? That means you see this equation, let me erase it for a bit clarity. Yeah, so if you will see this equation, so one thing of dimensionality reduction is subset selection. That means either you consider an input or discard it. But this is very discrete process. Okay, discrete process. The problem with discrete process, variance increases. Okay, so we don't want a discrete process. Rather, what we want all the inputs, but still we want to reduce the dimension. Another method to do this is shrinkage method. How we can do this? We can make this beta very small, beta or coefficient very small. If we can make this coefficient very small, so this input x3 will have very less effect on the output. Okay, so by that method, that is called shrinkage method. Okay, we are not doing subset selection, but we are shrinking the coefficient. By shrinking the coefficient, one thing, we are making it a continuous process. The previous one is a discrete process, but now we are making it as a continuous process. Okay, so we can do this by shrinkage method. Okay, so let's see how we can do this by shrinkage method. Yeah, we can do this by shrinkage method. Shrinkage method, we will give penalty to the coefficient. How we will give penalty to the coefficient? Our main aim to give penalty to the coefficient is to decrease the coefficient very small. If we decrease the coefficient very closer to 0, so that coefficient will have very less influence on the output. So by that we are doing one kind of dimensionality reduction. So there are two methods for this shrinkage. There are two shrinkage methods. One is ridge regression and there is lasso regression. Ridge regression, what we are doing in the ridge regression, you can see this thing. This thing is yi minus your that thing, yi minus your fx side. So this thing is your residual square, sum of square. Okay, this is residual sum of square. In residual sum of square, if we add that coefficient that we want to decrease, okay, so by that our RSS will increase. If RSS will increase, there will be a penalty. Okay, this penalty will decrease the beta value. So by that we can reduce the dimensionality of the inputs. Okay, so two methods are there, ridge and lasso. What is the difference? Ridge, whenever we are talking about ridge, this is a L2 regularization. L2 regularization means the penalty term that we will add. This term you already know from the first slide, right? This term you already know. But here here we are adding a penalty term, and that penalty term will be dependent on beta square. This beta j is that coefficient that we want to reduce. So this penalty term will be dependent on beta square. But in lasso regression, this is a L1 regularization. That means this beta term will be this penalty term will be proportional to beta. Here in ridge, this penalty term will be proportional to beta square. That is why it is called L2 regularization. In lasso, this penalty term will be proportional to this penalty term will be proportional to to only beta, that is why it is called L1 regularization. Okay, so this is a shrinkage method. Okay, this is second thing how we can reduce the dimension. We have the third and last thing how we can reduce the dimension is our principal component analysis. This is a feature extraction method. Okay, I have,
Excuse me.
yeah, yes
Sir,
please.
in which regression, like ridge and lasso, which
Yeah,
one we are getting minimal error, sir?
minimum error, if you will say minimum error, we will get with ridge regression.
Ridge regression.
Yeah, because
Okay.
it is a L2
Oh,
regular.
yes, so.
Yeah.
Yes, sir.
L2 regularization. L2 regularization. Lasso, there can be some instance in which the coefficient goes to zero. Okay, but ridge, there the coefficient does not shrink ultimately to zero. Okay,
Hmm.
lasso, there can be cases in which the coefficient
Shrink to
shrink
zero.
to zero, but ridge,
Okay.
there can be a cases in which the coefficient does not shrink to zero. So that is ridge regression. Okay, so ridge
Minimal.
regression you will find less error, but
Yes.
sometimes what you want dimensional reduction as your first priority. You are not thinking about error, you are only thinking about dimensional reduction. In that case you can go for lasso regression. Okay,
Okay.
because here the
But,
coefficient can go to zero. Okay,
mm, but in ridge we cannot go to zero. So
ridge,
that's why it is minimal.
yeah.
Okay, so thank you,
But
sir.
if we talk about shrinkage method actually we want for discrete,
Yes.
we want continuous. Okay, not
Con-
discrete, we want continuous things. So that is why we should prefer with ridge
Shrink.
regression, because here,
Yes.
yeah. So that
Yes,
is
sir.
the
Thank
thing. That is the concept. Now
Yes.
we are going to this principal component regression, principal component analysis, PCA. PCA is a feature selection. Subset selection is your feature selection. This is your feature extraction method. Okay, principal component analysis is your principal feature extraction method. So what we are doing in principal component analysis, this was introduced by Carl Pearson in 1901. We are reducing the dimension, but we are unlike subset selection where we are dropping. Here we are converting our input into a different input. We are converting our input such that those input which are very much correlated to each other, we are converting it into one input. We are converting it into one input, and by that we are reducing the dimensions. Okay, so so this is a type of feature extraction, not feature selection. This is type of feature extraction. So see this case. Okay, this is a number data set. This is we have two inputs, corner pixel and central pixel. But you see this graph very well. Corner pixel, at one corner pixel we are seeing the maximum variability in center pixel. Okay, so corner pixel, at one corner pixel we are getting maximum variability in center pixel. That means our center pixel is giving more variation. We can even eliminate this corner pixel. Okay, so that is the concept of PCA. Okay, wherever there is a variation in more variation in data, that variation we consider it as a different axis. Okay, so here you can see center pixel there is more variation in data, but corner pixel there is no variation in data. So we can reduce this two input into one input, that is only central pixel. Let's explain it by another example. Okay, there are two inputs, one is sepal height and sepal width, and these are the data points. Now here you can see there are two direction in which the variation is more. Here you can see in this direction PC1 the variation is more, and here you can see in this direction the variation is more. Other direction the variation is not more. So uh, we can convert this into this. That means we can convert this into two axes, PC1 and PC2. PC1 means this has more variation, that is why PC1, and this has less variation, that is why PC2. So that is our idea of principal component. Now you will say there are only two inputs and you are also converting it into two input only. So what is the use? Now example or visualization, I can only show you two inputs, but there are real life data in which we have 100 inputs. Okay, so 100 also we can reduce in 2 dimension or 3 dimension by this principal component analysis. Like you see this example. Okay, this example, this sugar level or your output is dependent on many variable like height, weight and BMI and etc etc. Okay, like say there are 100 inputs and there is only one input called sugar level. Now to visualize this data is a problem, and to store, there is a curse of dimensionality. One sentence we can say there is a curse of dimensionality. So we can remove this curse of dimensionality with principal component analysis. So those variables that are very closely related to each other, we can combine that into one input. Okay, and we can call it as one principal component. Similarly, we can call the second thing as second, we can the other set of inputs that are very much correlated, we can tell it at PC2. Similarly all this PC. Okay, okay, yeah. So this is the thing. Okay, so we can, like we have 100 data inputs, we can convert it into 5 principal component axes. Okay, PC1, PC2, PC3, PC4 and PC5. So this is the concept of principal component analysis. Now another important thing, I have also told that maximum 2 axes we can visualize well, but after 2 axes we cannot visualize well. So always we design our principal component in such that our variation is explained only by 2 or 3 principal component, that is 80 to 90% variance is explained by only 1 to 2 principal components. So we can rank this PC1 input, we cannot rank height is greater than weight, we cannot rank, but PC1 PC2 or principal component we can rank it. How we will rank it? The principal component that will take maximum variance, we will be considered as PC1, and then subsequently those inputs that has less variation, we will consider it as PC2, PC3, PC4, PC5 and so on. Okay, so this is this plot is known as scree plot. Scree plot is the plot between principal component and variance explained. So you can say in 2 or 3 PC, let's not go up to 3 also. What we do is 2 PC, we choose our principal component in such a way that PC1 and PC2 only explains 90% of our variance, so that we can easily visualize our data. So this is about principal component. So those who are in the meeting, any doubt till now? Any doubt, any part you want to ask again?
So next sessions, we need some problems regarding this PCS in the assignment they're asking.
Yeah, okay. I will consider it. I will
Yes, sir.
see the assignment and I will consider it.
Oh, yes.
Okay, so let's discuss the problems one by one. I have already discussed, but let's discuss again one and one. So in this, I encourage everyone who are in the meeting, kindly I will be showing you the question, and I kindly request you to guess the answers, and once you guess it, I will tell you the concept. Okay, so this is the first question. The parameter obtained in linear regression can take any value in the real space. Option A, B are strictly integer, C always lie in the range 0 to 1, D can take only non-zero values. So yeah,
Yes.
Can take any values in real space.
yeah, very right. We know, we have seen this input. Yeah, we have seen this input. This input is on R. Okay, that means this input can take any value in the real space. Okay, this input always will be on the R space. Okay, so this inputs can take any value in the real space. Okay, so can take any value in the real space. So option A is the correct answer. Okay, Now quickly go to the second question. Suppose that we have an independent variable x1, x2, xn and dependent variable that is y. Okay, now imagine that you are applying linear regression by fitting the best fit line using the least square error on this data. You found that correlation of x1 with y is minus 0.005. Now,
Answer A, sir.
yeah, hello.
Answer A.
Yeah, answer A. Any other guesses? Yeah, absolutely right. What happens is yeah, this x1 the correlation of x1 with respect to y is very less, that is minus 0.005. You can also consider it as beta. Okay, beta 1. Okay, so beta 1 is very small. If beta 1 is very small, then this x1 will have x1 regressing y on only x1 does not will not explain y. Okay, so this is the thing. Okay, so correlation means you can consider it as the correlation coefficient or coefficient. Okay,
Sir,
so yeah,
if beta is 0.005, then we can consider.
no, you 0.005 also you cannot consider
Sure. Yes.
because it is very small, right? The effect will be very small. Okay.
Yes, sir. Got it.
Okay, so
So
understood.
suppose that value may get changed because it increases means,
Can you please repeat?
see, now the value of y is minus 0.005.
Yeah,
So according to this, it is very least error. So that's why we chosen that first option.
yeah.
Suppose the given y is the value is get changes. They may get increase. Suppose positive. Then
Y,
what will be the answer?
this is not the value of y or x, this is the value of beta. Okay, if
Okay, a coefficient. Yes.
yeah, if beta is increases, let's say
Mm,
it increases to something, so
mm,
it increases to 5. Okay, uh, this
yes.
can be your equation, right? Y equals to, let's say, 4
Mm,
plus 5x1 plus 10x2. So if you will regress only on y, there is a significant effect, right? 5x1.
mm,
But if
mm,
5 we are replacing with 0.005, so it does
mm,
not have significant effect on the y.
mm.
Okay, so this is the only thing that is asking in the question.
Okay. Thank you.
Okay,
The coefficient, the correlation one can be both positive and negative, right?
yeah, coefficient can be both positive and negative.
So the correlation.
Yeah,
Uh,
correlation or coefficient, coefficient you can say that can be both positive as well as negative.
and is it that it should be within 100 or it can be any value like 1,000, 10,000?
Any value, any value, but see, what happens in real model, we want our beta naught to be as small as possible. Why we want our beta to be as small as possible? Because we want that beta should be uniformly distributed to all the inputs. Okay, so one input, if it will take very much value, there can be a problem of variance. Okay.
Acha, yes.
Okay. Okay. So option A is the correct answer. Okay. Now moving on to the next question, the relation between studying time in hours and grade on the final examination, 0 to 100 in a random sample of students in the introduction to machine learning class was found to be this. This is your machine learning model, that is fx equals to beta naught plus beta 1 x1. Okay, what is x1? X1 is the studying time in hours. What is fx? Fx is your grade. Okay, now it is asking us how will a student grade be affected if studies for 4 hours compared to not studying. So so not studying means x equals to 0. 4 hours means x equals to 4. So when we will put in this equation f equals to 0, x equals to 0 or f0 will calculate, the answer will come 30.5 because 15.2 into 0 is 0. So the answer will come 30.5. Now if we will put x equals to 4, or we will calculate f4, that will be coming 30.5 plus 15.2 into 4, that means 30.5 plus 60.8. Now we are asked how will the student grade be affected. Okay, so we are basically asked to find out f4 minus f0, this thing already written, f4 minus f0. Okay, that we have to find out. So f4 minus f0 will be equal to 30.5 plus 60.8 minus 30.5, that will be equal to 60.8. That means the grade will increase to 60.8 points if the student will study for 4 hours compared to not studying. Okay, so option B is your correct answer. Okay.
Sir, if someone studies for 5 hours, then will this model become invalid?
No,
Like it will
this
exceed 100
why this model will become invalid? 5,
because it
x
will.
equals to 5, if you will put 15.2 into 5, that means it will okay, yeah, true, yeah, I got it what you are asking. Yeah, it is true,
Yes, sir.
because the space is given 0 to 100 only. Okay, so
Yes,
that
sir.
is why. Okay, okay, nice, good observation, nice. So let's move to the question number 4. Consider the following 4 training examples. We want to learn a function fx equals to ax plus b, again a linear regression problem. A squared error at the loss function. Which of the following parameter would you use to model this function? So we want squared error. We want the least squared error. Okay, so how we find out the least square error? We can find out the least square error by optimizing the beta. How we can optimize the beta? We can make this yeah we can take the help of this matrix form. Okay, how we can make this as a matrix form? We have one input. Okay, one input minus 1 0 1 2. Okay, we have one input, and we have yeah, we have actually 4 data points. That means n equals to 4. Okay, we have 4 data points, n equals to 4, and we have one input. One inputs mean p equals to 1. Okay, so x matrix will take n cross p plus 1, that I have discussed in the first slide. X will take n cross p plus 1. So n means we have 4 data points, so our matrix will be 4 cross p plus 1. Okay, so p plus 1. Why p plus 1? Because again here you can see there is a intercept, or there is a beta naught. If there is no beta naught, then we can take n cross p only, but here as there is a intercept, so we will take n cross p plus 1. Okay, so by that we will find the x matrix. So this whole will be your x matrix. Okay, this thing will be your x matrix. Okay, this thing will be your x matrix. This thing will be your x matrix. Now how we can find out the beta so that our model becomes the best fit? That is equals to xt xt, or transpose of the x matrix, into x whole inverse into transpose of x into y. Yeah, what will be the y? Y will be your n cross 1 matrix. So y will be your 4 cross 1 matrix. So this will be y. So by that you can find out the beta values. Beta values, how we can find out? You know the x matrix, right? So you can find out the x transpose matrix. How we can find out transpose? By converting rows into columns and columns into row. So xt is 4 cross 2 matrix, right? This xt is, sorry, x is 4 cross 2 matrix. Now x transpose will be 2 cross 4 matrix. So our xt into x will give 2 cross 2 matrix. We will inverse this, again it will give us 2 cross 2 matrix, and then we will multiply
Sir,
it
please,
by, yeah,
sir, please tell me this X inverse once again, sir. I'm not getting this.
inverse.
Yes, sir.
Inverse is you have to go to matrix thing. So matrix, so inverse of any matrix, so x inverse equal to adjoint of x, adjoint of x by x, x magnitude of x. So this is the inverse thing. Okay, this formula you got, right? This formula is from first slide only. This is your formula. Okay, This is your formula, x transpose x, inverse of it x transpose into y. Okay.
Yes, sir.
Okay, formula you got. Now you got the x matrix. You got the x matrix, right? How we are forming the x matrix? This is your x matrix. X matrix will be n cross p plus 1 order. Okay. So n means data points. Okay. Yeah, n means data points, so number of data points are 4 here. P means number of inputs, that is p is 1. Okay, so your matrix will be 4 cross 2. Why not 4 cross 1? Because here we have extra intercept,
Plus
that is,
1
yeah,
coefficient beta.
yeah, that is why 4 cross 2 matrix, you can form the 4 cross 2 matrix, right? This is your 4 cross 2 matrix. Now transpose you can find out, that is 2 cross 4 matrix, that is converting columns into rows and rows into columns. So x transpose also you can find out, you can multiply it and you can find the inverse. So this thing you can find out, and your matrix will be of the order 2 cross 2. Now x transpose will be ordered 2 cross 4. Now 2 cross 2 into 2 cross 4 matrix means you will get a 2 cross 4 matrix. Now when you will multiply it by y is your this matrix, this is your y matrix. Okay, that is n cross 1 matrix, that is 4 cross 1 matrix. So you will find a 2 cross 1 matrix. This 2 cross 1 matrix, this will be equal to your beta. Okay, beta cap. Okay, and this will be, let's say it will be alpha theta. Okay, this will be alpha theta, this beta cap. So alpha will be equal to beta 1, or in this beta 1 b, and theta will be equal to beta 2. Beta 2 is your a. Okay, so you got this equation. Now you will find a and b. This is your a, alpha will be a, and this theta will be b. So you got a and b, so you got this fx. So you can solve it. But the problem with this question is they have given a and b. So there can be a situation in which this a and b that you have calculated will not be according to this option. Okay, there can be a problem, because the a and b can come in points, and that may not be satisfying the options that has been given in your question. So how to deal with that? So for that we should go to approach number second. How? What is our approach number second? Approach number second is we take this value 1 1. That means a equals to 1 and b equals to 1. So our first machine learning model will have this equation, fx equals to x plus 1. Okay, this will be our first machine learning model equation. Now we have actual output, that is yi, we know that is 0.319. So yi minus fxi. So by that we can find out the error. What is error? Error is actual minus predicted, that is yi minus fxi. But in machine learning, what we know, that we are always interested in squared error. Okay, squared error, that is why yi minus fxi square. So we will do this for all the data points. That means for first data point, second data point, third data point, and fourth data points. So we will find out RSS1 by this thing. Okay, by this thing or this equation. Similarly, we will find the fx2. What will be our fx2? Fx2 will be this. Fx2 will be a equals to 1, that means x plus 2. This is our fx2. So we will do the RSS2 with fx2. Okay, RSS2 with fx2. Similarly, RSS3 with fx3, RSS4 with fx3, fx4. Okay, so we will compare the RSS, which one will have the least RSS, that is which one will have the least error, that we will be considering. Okay, so whenever we will do the RSS, you can see the option A will have least RSS, so that will be your answer. Okay, so option A is your correct answer. Is it clear? Any doubt in this? Hello? Any doubt
Yes.
in this question?
No, sir.
Okay. So let's move on to the next question. Consider the modify KNN in which one of the k nearest neighbor to the query point are identified, you do a linear regression fit on them and output the fitted value for the query point. Which of the following is are true for regarding the method? Okay, what is KNN? How we can calculate KNN? Unlike linear regression where we find a function, KNN we don't find a function. So then how we calculate our predicted output? What happens is KNN we take the help of nearest neighbor. Like we have 4 data points, x1, x2, x3, x4. Like we are asked to find the value of one data point that is between x2 and x3. Let it be x2 dash. So how we can find it? We can find it by KNN. KNN means we will consider the neighbors. How many neighbors we will consider? That depends on the k value. Let's say the k value is 2. So we will consider 2 data points that are that are in neighbor to this x2 dash, that is x2 and x3. So we will see the output of x2, that is y2. We will see the output of x3, that is y3, and we will mean it. That means y2 plus y3 divided by 2 will be equal to your y2 dash. That will be your answer. So that is KNN. But in this question what has been asked is a modified KNN, not KNN but a modified KNN. How they have made modified KNN? Once they found out the nearest neighbor, they have fitted a linear regression model, and then they are telling which of the following is true regarding this method. So first thing, this method makes an assumption that data is locally linear. Now if the data is not linear, you cannot fit a linear regression model. So option A is correct. Second, in order to perform well, this method would need dense distributed training data. Now if the variance is more or the data is very much sparse, okay, so if the data is very much sparse, you cannot locally fit the data. Okay, you cannot locally fit the data, and that too with a linear regression. So that is why in order to perform well, this method would need dense distributed training data. So option B is also correct. Option C, this method has higher bias compared to KNN, and option D, this method has higher variance compared to KNN. So if we compared with KNN, modified KNN is more complex, and in previous class I have discussed this graph, okay, which graph? A graph in which the more complex is the model, bias becomes less but variance increases. But more simplest is the model, bias is more but variance is less. So modified KNN is more complex than KNN. Okay, so as modified KNN is more complex than KNN, that means modified KNN will have higher variance and lesser bias. Okay, so option A, B and D is your answer. Okay, is this clear? Hello, is this clear?
Yes, sir, clear.
Yeah.
Yes.
Yeah, so question number 6, which of the following is a L2 regularization? Option A, raised regression, option B, lasso regression, option C, both A and B, and option D, none of A and B. So I hope everyone know this, L2 regularization and L1 regularization. Lasso is your L1 regularization, because the penalty term we are using, it depends on beta, but ridge is our L2 regularization. That means the penalty term is beta square. Okay, penalty term is proportional to beta square, so that is L2 regularization. Here in the question we have been asked L2 regularization, so option E is your correct answer. Okay, so is this clear?
Yes, sir.
Okay.
Yes.
Now coming to question number 7, choose the correct option. Which of the following are correct? When working with a small data set, one should prefer low bias high variance classifier over high bias low variance classifier. When working with a small data set, one should prefer high bias low variance classifier over low bias high variance classifier. Option C, when working with the large data set, one should prefer high bias low variance classifier over low bias high variance classifier. And D, when working with the large data set, one should prefer low bias high variance classifier over high bias low variance classifier. Which option is the correct option? We have to take which option is correct option. So So see, here there are two things that has been asked: small data set and large data set. So in case of small data set, what we are interested, we are interested in low variance. We know there will be more bias because we are only dealing with very less number of data points. So we know there will be error, but we want our variance to be small. Okay, so so when working with small data set, we want high variance but low bias over yeah when working with the small data set, when working with the small data set, we know that bias would be means error would be large, but we required low variance. Okay, so option B is correct. Now when working with the large data set, you will see, when working with the large data set, we know that data set can be very much spread. Okay, so variance, we know that variance can be large, but as we are dealing with a large data set, we require our bias to be small. So when working with large data set, we want low bias and high variance. So option B and option D is your correct answer. Okay, is it clear?
Yes, sir.
Okay, so question number 8, consider the following statement. Statement A: in forward stepwise selection, in each step that variable is chosen which has the maximum correlation with residual, then the residual is regressed on the variable, it is added to the predictor. Statement B: in forward stage-wise selection, the variables are added one by one to previously selected variables to produce the best fit till then. So option A, both the statement are true. Option B, statement A is true, statement B is false. Option C, statement A is false, statement B is true, and option D, both the statement are false. Now can anyone guess? Already I have ticked it, but yeah, see, statement A, forward stepwise selection. What we do in forward stepwise selection, we first choose an intercept and then add
One by one, I think.
1 by n 1. Okay, and forward stage by selection, again we start with the intercept, but then we
With
add
correlation.
a input that is closely correlated with the
Residual.
regressed value.
Yes,
Okay,
sure.
so that is why but here you can see in the statement, here it is reversed. Okay, forward stepwise selection, it is telling residual of the regress is mentioned, and here forward stage wise selection, here they are only adding input one by one. Okay, so both the statement are false. Okay, the correct statement is reversed. Okay, reverse, when you will reverse it, you will find the correct statement. So option D is correct. So any doubt in this? I hope no doubt in this. Okay, let's move to the next question. Question number 9, the linear regression model y equals to a naught plus a1 x1 plus a2 x2 ap xp is to be fitted to set the and training data points having p attributes each. Yeah, very similar to this first slide what I have discussed, only here they have played with the variables. We have discussed with beta naught, beta 1, beta 2, etc. They have discussed with a naught, a1, a2, etc. Okay, and same thing, other things are very much same. We have told this beta naught, beta 1, beta 2 as beta, but here beta vector, but here they have told this a naught, a1, a2, ap as theta vector. Okay, so we know this equation. RSS with respect to beta is y minus x beta, y minus x beta. Okay, now if we replace beta with theta, we can get y minus x theta transpose y minus x theta. Now if we can differentiate it, we will find this xt y minus x theta equals to 0. Now we can solve this x transpose into y equals to x transpose into x theta. So option D will be our correct answer. Okay, is this clear? Is
Yes,
this
sir.
clear? We have discussed in detail in the first slide. So very exactly similar. Only here they have replaced beta with theta, and theta is a naught, a1, a2, etc. Okay, only this difference. So let's move on to the last question. Let n cross n be a matrix of real number. The matrix A transpose as a eigenvector x with eigenvalue b then vector y of ATA will be which has eigenvalue b is equal to. Now what they have given a matrix and they have given eigenvector as well as eigenvalue for this matrix. Now for another matrix, what they have asked if they have only given in this case eigenvalue, and they have asked what is the eigenvector. Now there is a property of a matrix. Okay, what is the property of a matrix? Matrix into the eigenvector is equal to eigenvalue into the eigenvector. Okay, again I am repeating, matrix into eigenvector is equal to eigenvalue into eigenvector. That is a property of the matrix. So for this matrix, if we say, so matrix AAT into the eigenvector, that is AATX, will be equal to eigenvalue into b into eigenvector, that is bx. So up to this I think clear. Now what they have asked to find out the eigenvector of ATA. Okay, so how we can find out the eigenvector of ATA? If we can multiply AT or A transpose on both sides. So if we could multiply A transpose to both sides, we will be getting this. Now if we simplify it, we can make ATA into ATX equals to B into ATX. Now this is of the form this. How this is of the form? We can consider this as a matrix, which is a matrix, and then this is a eigenvector equal to eigenvalue into eigenvector. Okay, so we have been asked to find out eigenvector of ATA. So eigenvector of ATA will be equal to ATX. Okay, so option B is your correct answer. Okay, so is this clear?
Yes, sir.
Okay.
Yes, sir.
So any more doubt for today's session? Okay,
No, sir. Clear, sir. Thank you, sir.
okay, so this will be available on that YouTube channel, this discussion, whatever we have done. Okay, this will be available. Also in that folder you will find this slide, as well as there is a reference book also kept for you for the mathematics thing, because those lectures has so much mathematics in it. So I have put a reference book for all of you. Okay, in that folder. Okay, so by that I am ending the session for today. Okay.
Yes, sir. Thank you so much, sir.
Thank you, sir.
Okay, bye everyone, bye.